Okay. Well. Good evening, everyone. Welcome back to our Morocco HPC webinar series after a short break. So we took actually a short break, and I want to take this occasion to wish everyone a happy new year. And I hope you all have a year filled with happiness and success. And I hope that we all witness the growth of Morocco HPC in 2025. So for those of you, again, who do not know what Morocco HPC is, or if this is your first time or the first time that you hear about us. So Morocco HPC is actually a gathering of HPC researchers, HPC professionals, practitioners, or simply HPC enthusiasts to share and collaborate. So Morocco HPC is actually dedicated to building a vibrant community that explores and also discovers the power or the role of high-performance computing in research, innovation, and different fields. So we are trying to do that by organizing a large number of events or having a large number of initiatives. And one of them is actually our webinar series. So tonight, I am very happy and very pleased to be moderating a session with Dr. Adnan. So Dr. Adnan is actually a distinguished researcher and an assistant professor with the College of Computing UM6B, with a career that is actually amazing. It's literally mind-blowing. So when I read through it, it's really, really amazing. He's been through a lot of leading institutions, been through a lot of competitions, won or was qualified to different awards. So we are really, really happy to have you with us here. So Dr. Adnan will bring actually a wealth of knowledge about different approaches to transform the world of cyber-physical systems, which is actually his domain of expertise. So there's actually no one better than Dr. Adnan to talk to you about cyber-physical systems and what are the different approaches within this entire field. So we are really thrilled and thank you so much for accepting this invitation. And we're really happy to have you with us as Morocco HPC continues to share and as we continue to collaborate in the HPC field. So let's dive into this topic and discover what you have to share with us. So thank you again for joining us and let's get started. So Dr. Adnan will actually be waiting for your questions or comments. So we invite you to type them in the chat and we're gonna make sure to take them as soon as they come in. So, Dr. Adnan, thank you very much for joining us today, and the floor is yours.
Yeah, thank you very much for the invitation, Safa, and for the nice introduction, and thank you a lot for your efforts to promote this HPC culture in Morocco. So my talk will be on safe and guaranteed machine learning for the control of cyber-physical systems. So first, I will start by presenting what are cyber-physical systems, what are the main challenges in cyber-physical systems, and then I will be explaining somehow the complementarity between machine learning and control, in the sense of how we can use tools from machine learning to solve some open problems in control, but also how to use some tools from control to solve some open problems in the machine learning community. And yeah, please be interactive. So whenever you have a question, you type it in the chat, and once I receive the question, I can provide an answer. I mean, you are not obliged to wait until the end to provide your questions. Okay, so let me first briefly describe what do I mean by the term cyber-physical systems. So cyber-physical systems, they're all entities that are consisting of a physical part and the cyber part. Okay, for example, if we consider an autonomous car or a robot, so the robot or the dynamics of the robot, the mathematical model of the robot is described by some physics laws that we can get, for example, from the first principles of Newton. But then the robot also consists of a cyber part, so it may contain microprocessors, microcontrollers, sensors, etc., so that it can interact with the environment, it can interact with other robots, and then we can control the robots, etc. And the cyber physical systems today are this class of systems consisting of physical parts and the cyber part. Okay. And then, as I said, so cyber physical systems, they're very present in modern society. So we talk about smart vehicles, smart buildings, smart grids, smart traffic, etc. So we have a lot of applications cyber physical systems in our modern societies. But at the same time, you have the machine learning community that is somehow presenting very efficient tools with also the ability to deal with very complex systems. Okay, so those progresses somehow in the machine learning community have motivated researchers from the control community to use machine learning to control cyber physical systems. Okay, and then how machine learning can be used in the context of control, I will be explaining this through simple examples. We have this example here, which is called ACC, adaptive cruise control. So it is a classical problem in control. So in this problem, we have a leading car, and then a following car. Okay, and then the objective is that we want to control the following car to ensure some minimal security distance, okay, to ensure safety of both cars. And we are doing this by controlling this car. Okay, at the control level, how this problem can be formalized? It can be formalized through this picture, where we have the physical process. So the physical process is the mathematical model of the car. And we have a control software. Okay, the control software is just the algorithm that is implemented in the microprocessor or the microcontroller, the system that is controlling the car itself. Okay, but now if we want to use machine learning to solve this control problem, there are three different aspects, or three different ways somehow. So the first way is that we assume that we do not know the mathematical model of the car. Okay, and we will model it, for example, from data using neural network model or Gaussian process model or any other type of model. So we're going to learn this model from data, and then we're going to use somehow the classical control tools in the control community, PID controllers or any type of control. Okay, but we can have some sort of also complementary strategy. So in this complementary strategy, so we can start from the case where we have the mathematical model of the car, but we want to learn the controller. Okay, for example, using tools like model-based reinforcement learning, where we know the model and we want to learn the controller. But we can also have the third scenario where we do not know the model, but we want to learn at the same time the model and the controller. We want to learn both and in parallel. Okay. Now, what is the issue with this? So the issue is that just using learning in a direct way, okay, so just using learning in a direct way without adding some verification, supplementary verification layer, we cannot have guarantees that the system will be safe. For example, if I take the model of my car, I know the model of my car, I will use reinforcement learning to learn a controller that will ensure a minimal safety distance. But at the end of the training, when I take the controller that I learned, for example, from through reinforcement learning, I do not have any guarantees or any proofs that the learned controller will provide safety for this case and will allow me to avoid collision. Okay. Same, if I'm going to learn a neural network model of the system, and then I use it to design a controller, I do not have guarantees on how the neural network model is representative for the system. And since I cannot measure how this neural network model is representative for my system, I cannot have some sort of guarantees at the end on how the system will be safe. Okay, and this is the research problem I have been working on recently, starting from the end of 2019, which is how to provide safety when using machine learning for the control of cyber physical systems. Okay, so we want to use machine learning in the control, but we want also to have some sort of formal guarantees or proofs that nothing bad will happen. For example, here, we want to have proofs, mathematical and algorithmic proofs, that the vehicle will not collide with the other vehicles and not collide with other obstacles and will not collide with pedestrians, of course, etc. Okay, so this is the general problem I will be presenting in this talk. And to address this issue, there are different tools. So here, what I will be presenting some sort of, as I said, complementarity between machine learning and control. Okay, so I'll present the first scenario where we do not have the mathematical model of the system. Okay, we just have data. And then from this data, we want to construct a model, learn a controller. Okay, but we want also that the system, we want to show somehow that the system is safe, or that the system will satisfy the specification with some probabilities. Okay, and then to achieve those probabilities, we'll use tools from machine learning, such as some statistical learning tools. Okay, that's the first problem. So this is a problem where we're going to use tools from machine learning to provide a solution to an open problem in the control community. And then from the other side, on the complementary side, I will present in second problem, so on which we have the physical process. We know the mathematical model of the system, but now we want to use, for example, Q-learning to satisfy some objective, and then be presenting how we can use tools from control, okay, to ensure or to provide some guarantees that the learned controller with reinforcement learning will indeed satisfy the given objective. Okay, so first I will start by presenting, or what we call in general symbolic control of cyber physical system, and which is one of my main research directions. Okay, so the first definition I will start with is what is the specification for a cyber physical system.
Okay. Dr. Adnan, before you get into the definition, can we take a question?
Sure, of course, yeah.
Okay, so Dr. Ahmed is asking, could you please give us an example of the physical model?
Okay, so the physical model, for example, physical model of the drone, you can just write, or a robot, for example, you can just start from the first principle of Newton, and then you can get, at the end, you will end up with some sort of differential equation. Okay, and this differential equation, in general, it will be describing somehow the behavior of the robot or the drone, for example. If you start from an initial condition, it will satisfy some differential equation, and then you can get what is the trajectory of this robot or drone, for example. But that's one example of a model, but you can have some more complex model, for example, some PDEs or other types of models.
Another follow-up question. So did you try to combine both physical laws and data?
Yes. So the thing is that in general, how things needs to be done is that if you have physical laws, yes, you need to start from them and then complement them with data to learn, for example, just some parameters. For example, if you want to model a car, you can use physical principles to have a model of the dynamics, but then there are some parameters that you may not know. In this case, you can use data or learning just to learn those parameters. I mean, you need to exploit the fact that you have the physical models.
Okay, thank you. I think we can continue until we get another question.
Yeah, thank you for the question. So yeah, as I said, we have some specification. Those specification or objectives can be in general very complex. For example, I have a drone. I want the drone to pick up a packet from location or region A, drop it in a region B within 30 minutes, and then avoid the obstacles. And then when the battery is low, go to a charging point and stay there for 2 hours. So this is a complex objective. And then we want the robot to do this in an automatic way. Okay, so we want the robot to learn somehow a controller, or we want to design a controller to make the robot do this objective, satisfy this objective in some sort of automatic way. Okay, and then the type of models there, as I said, there are different types of models, but I will focus on two specific type of models. So they're what we call in general continuous representations, and they are discrete representations. Okay, so in continuous representation, those are represented in general, for example, using difference equations. So what this equation mean? For example, it means that if your system is a robot, okay, X is the position of the robot. and U is the input you apply to the robot. Okay, how you make your robot act. Okay, and this equation here, it means that if the position of the robot at time k is x of k, and if you apply at time k a given input u of k, then the robot will move to this position at time k plus 1. Okay, it tells you now if you start from a state, you apply an input, you will move to a next state. Okay, but this representation is continuous because here the variable x belongs to the set. For example, if you consider a mobile robot, it belongs to R2. Okay, so it's x and y axis, and the robot can move continuously. Okay, so x belongs to R2, for example. And we can have also what we call discrete representation. Okay, so in discrete representations, the model is a graph, okay, where the positions are, for example, predefined, and you can move from this position to this position, but you cannot move to any position in between the two positions. Okay, so in general, this type of models have been extensively used, I would say, in the control community. So in the control community, researchers are more, in general, focusing on this type of model that are defined on a continuous basis. From a formal methods community, computer science, researchers are more using this type of discrete representation. While here, for example, the set of states and the set of inputs are finite in general. Okay, so in symbolic control, how do we proceed? So in symbolic control, we start from a continuous model and we build a discrete model. Okay, so what we do in general is that we start from the real model of the system, which is a complicated model. We abstract it to a simplified model. We construct a controller for the simplified model. And finally, we transform the controller for the simplified model into a controller for the original system. Okay, and which type of mathematical formalism we use to model the system and its abstraction? So in general, we have differential equation of this form, or a differential equation that we can discretize, or sometimes NDP that we can discretize also, both in space and in time, to get to this type of models. Okay, and once we have this type of model, we go and construct the abstraction, which is a graph or an automata of this form. And then the advantage here is that once we have this discrete representation, we can use tools from formal methods community to construct the controller. Okay, so that's the flow chart somehow of the symbolic control. So we start from model of the system, we construct an abstracted model, we construct a controller for the abstract model, and finally we transform it to a controller for the real model of the system. Okay, so now the main question here is how we construct this abstraction. So how we go from this continuous world to this discrete world. Okay, so I'll be explaining this on this slide. So now assume that my physical system is described by this differential equation. Okay, and assume, just to simplify, that my model is a robot. Okay, a robot that is evolving on this region. Okay, a mobile robot that is evolving. This is the x-axis, this is the y-axis, and the robot is evolving on this region. So this is our state space x here, the state x. So the first step is that we discretize the state space into a finite number of regions. Okay, for example, here we have 16 regions, 4 in each dimension. And similarly, we discretize the input set u into a finite number of inputs. For example, if my set of inputs is the set 0, 1, continues from 0 to 1, I can discretize, for example, to 11 values, for example, 0, 0.1, 0.2, etc., until 10. Okay, so now I have my discrete states for the abstraction, and I have my discrete inputs. But now how do I compute the transitions? So what do I mean by transition is how my abstraction will evolve, in the sense that if I start from this discrete state and there are given input, to which state I will move. Okay, and here we use what is called the reachability analysis. Okay, so let me explain what do I mean by the term reachability analysis. So for example, if I start from this cell here, so this cell, it represents this region here. Okay, so what I do is that I compute the reachable set from this region under the given control input, which corresponds to this region. So what does this reachable set mean? It means that if the robot is in this region, for example, at time k, then at time k plus 1, it will be in this region. Okay, for example, if in 10 seconds my robot is in this region, then in 11 seconds my robot will be in this region. Okay, so this is the reachable set, means that if I can start from the set under this difference equation, I will reach this set in one time step. Okay, so now once I compute my reachable set, I can see, for example, here that that my reachable set is intersecting with those three regions. Okay, so this means that at the level of my abstraction, that if I start from this region, I can go either to this region, or to this region. Okay, so I have three possibilities in parallel. I have some non-determinism here. Okay, so this is my abstraction is called non-deterministic because I do not know to which region I will be going exactly, but I know that I can go either here or here or here at the same time. Okay, and so now you can see that my abstraction is somehow representative for the system. For example, because you can see that for any behavior of my original system, for any trajectory, if I start from a point and I reach a point, I have some trajectory or transition at the abstraction that reproduce the same behavior. Okay, for example, if I start from here and I reach this region here, then I'm reaching this cell and I'm reproducing this behavior at the level of the abstraction. If I start from here and I reach this region, again, I'm reproducing this behavior. Okay, so now what is the advantage of symbolic control? The advantage is the following. So I start from the physical system, I construct the abstraction using this procedure, but now given a specification phi or a control objective, if I can construct a controller for the abstraction for this simple model or simplified model, then I can transform it to a controller for the original system. Okay, so that's the main advantage, that I can start from this model, construct the abstraction, construct the controller for the abstraction, and then transform it into a controller for the original system. Okay, so this is as I said, the general approach of the symbolic control, which is summarized here in this slide. But now all this approach is working well if we know the dynamics F. Okay, because if we know the map F, then we can compute this reachable set. Okay, there are many papers in the literature that present different approaches to compute this reachable set when we know the map F. Okay, but the problem we have been dealing with is how to proceed where we do not have the map F. Okay, we do not know what is the mathematical model. We just have some sort of data points. We want to start from those data points, construct the abstraction, okay, but to also have some sort of guarantees, okay? And the problem we have been addressing here is to have some sort of probabilistic guarantees. What is the number of data points that is required? Okay, and then to solve this problem, we have been using tools from statistical learning. Okay, so now I'll be explaining this main problem. So we start from data. We want to construct a symbolic model from data, an abstraction from data, but then how our abstraction constructed from the data can be representative for the original system. Okay, and we found some sort of closed form or closed expression on the number of required data to achieve some sort of or some given probability. Okay, so this is the main issue we have been dealing with here. So we have a system, we do not know the model of the system, we're just using data points, and we want to construct the abstraction and then the controller. Okay, so now the first point is, what are the data points here? Okay, So assume that I have a nonlinear system of the following form. Okay, as I said, for example, if I'm considering a robot, so this differential equation means that if the robot is at this position at time k, and they have applied a given input at time k, then it will move to this position at time k plus 1. Okay, so here I'm considering the map F as an input-output map. Okay, with inputs and an output. So the inputs are the position, for example, of the robot, and the input we apply to the robot, and then the output will be the position of the robot at the next time step, at time k plus 1. Okay, so those are our collection of data points, input data points and output data points. Okay, so now this is the algorithm we use to construct our abstraction. Okay, so how we proceed, like what I presented before. We discretize the space into different regions. Okay, now from each region, now instead of computing the reachable set, because we cannot compute it, we are just sampling. Okay, sampling some m continuous state from this region. Okay, according to given probability, and then we're computing the successor for each of these points. Okay, for example, if I want to run this experiment on a robot, so I will start from this region. I will start the robot from different positions. Okay, for example, if the robot starts from this position, it will reach this position. If it starts from this position, it will reach this position, and so on. And I keep collecting data points. Okay, so now each starting point here in black have a successor here in red, which means that if you start from this position, you will reach this position. Okay, and now whenever I'm reaching a position that is intersecting with some cell in the grid, I'm adding a transition to this cell. For example, if I start from this point here, I'm reaching this point here, which belongs to this cell. So I'm adding a transition to this cell here. If I start from this point, I'm reaching this point, which belongs to this cell. So I'm adding a transition to this cell, and similarly for this one. So now, since all the points that I can reach, or the red points that I collected, belongs to those three cells, so then I'm adding transitions to those three discrete cells here at the level of my abstraction. Okay, but now one may see here that, okay, I can start from another point, which is not among my data points, and reach another cell. For example, go there. Okay, and this is why we will be providing these probabilistic aspects of our guarantees. Okay, because we are not taking into account all the possible scenarios. So we're just sampling some data points. Okay, and then through those data points, we're getting some decision. And then using statistical learning, we can provide some sort of bounds on how much do we trust the decision that we get based on the data points. Okay, and here, so one of the main points to relate things to HPC is that this process here can be easily parallelized. For example, I can start experiments from one region, another region, and then another region. So I have some sort of parallel structure of my problem. And here, HPC platforms can be indeed a good tool to use in this, or to deal with this type of problems. Okay. So now, as I said, using this procedure.
I have a quick question about the parallelization on HPC platforms. Did you try the parallel processing of?
Yes. So here's the thing. So when I did this work, I was doing my postdoc at UC Berkeley, and then we used HPC platforms there to parallelize this code.
Okay. And so I think you did it to compare to the parallel and the non-parallel, or just to accelerate?
No, to accelerate. No, to accelerate this process of construction of the abstraction. Because so is the thing. So this is here. The system is very simple. We have 16 states, but in general, the system is made of millions of discrete states. Among discrete states, you need to get some data points. So yeah, there were need to parallelize and to use HPC to do this or to go through this procedure in a more fast and efficient way.
Okay, thank you.
Okay, so yeah, now as I said, using this procedure we can construct the abstraction, but how good is our abstraction? What we can guarantee about our abstraction? And the thing we provided here is the following theorem. So this was the main result of this work, which states that now if I fix some accuracy parameters mu and confidence parameters delta, so those are probabilities that I will explain later in the numerical example. But the problem was the following. So now once I fix the accuracy parameter mu and the confidence parameter delta, if the number of data points satisfy this inequality, okay, where nx here is the number of discrete states. For example, here I have 16 discrete states, and nu here is the number of discrete inputs. For example, for this experiment, we have chosen 3 discrete inputs. So if the number of data points is greater or equal than this quantity, then if I can construct a controller for the abstraction to satisfy specification, then I can transform it to controller for the original system such that I will have a probability that the concrete system will satisfy specification phi greater or equal than 1 minus mu with the confidence 1 minus delta with respect to the data points. Okay, so now I'm not just getting data points and then running the abstraction on them and then constructing the controller, but I'm saying also that if I want to achieve a given probability, okay, this is the number of data points that is required. Okay, and you can see, for example, here, if you want mu to go to 0, the number of data points needs to go to infinity, and if I want the confidence parameter delta to go to 0, again, the number of data points needs to go to the infinity. Okay, so one might ask here, what does it represent, or what does it mean, those accuracy parameters mu and confidence parameters delta? Okay, so I'll be explaining this on a simple examples we have been working on. So I've been considering the dynamics of a kinematic model of a marine vessel. So we have a marine vessel model. It's a ship. Okay, it's a ship described by a difference equation, and the map F here describing this difference equation is unknown. Okay, and we have a state of the ship which consists of 3 variables. We have x1 and x2, which are the planar positions. So those are just the position with respect to the x-axis and y-axis. Okay, and we have the hidden angle, which was the orientation of the head of the ship. And we have some control inputs, 3 different control inputs to control our ship. Okay, and then for this model, so we had the following control objective. Okay, so we wanted our ship to start from anywhere in the space in this white region, avoid those obstacles, and reach this target region. Okay, and then what we have been done. So yeah, so I forgot to mention. So we want the ship to reach this region in less than 2 minutes. Okay, start from anywhere in the space, avoid those obstacles, and reach this region in less than 2 minutes. Okay, and as I said, we didn't have a mathematical model of the system. Okay, we can just run the model and then collect some data points from the trajectories. Okay, so then we have went through this procedure I explained now. So we constructed the abstraction according to algorithm 1 using data, and then for the abstraction we fixed the following parameters. So we have a confidence parameter which was 10 to the power minus 6, and then the accuracy which was 0.1. Okay, and then according to our theorem, the number of simples was something almost 24,000 data points required. And then once we constructed the abstraction, here we use tools from the formal method community, fixed point algorithm, and such stuff to construct the controller. Okay, And then once we have this controller, we're able to implement it on the system. And here we can see some examples of trajectories of the system. They can start from different regions, avoid the obstacles, and they reach this target region. Okay, but here the main point is, what do I mean by confidence parameter delta, which is 10 to the power minus 6, and accuracy mu 0.1? Okay, so I have two parameters here. So what does those parameters mean? They mean the following. They mean that if I run my system, okay, 1 million times, if I have 1 million scenario, and 1 million it comes from this 10 to the power minus 6, I will have at most one scenario for which the probability of satisfaction is lower or equal than 90%. And 90% it comes from this 0.1. Okay, so now if I change those parameters, for example, if delta is equal to the 10 to the power minus 9, and if the accuracy mu is equal to 0.01, what does this mean? It means that if I run my chip 1 billion times, 10 to the power 9 times, okay, I will have at most one scenarios for which the probability of the non-satisfaction of the specification is greater than 0.01. Okay, which means that the probability of satisfaction is greater than 99%. And what is the probability of satisfaction? Is the probability of avoiding the obstacles and reaching the target in less than 2 or 3 minutes. Okay, so this is the main idea here, is that how we can construct a controller using symbolic control from data, because we do not have a mathematical model, but also how we can provide some sort of statistical guarantees that nothing bad will happen. Okay, so now I will move to the last part of the talk. Okay, and this part is more related to Q learning or reinforcement learning. Okay, so as I said in the previous part, I showed how we can use statistical learning to solve those data-driven control problems. So here I will be explaining how we can use symbolic control techniques, which is a tool from control, to solve some sort of open problems in the reinforcement learning community. Okay, so we have the following problem. So physical process, we have a mathematical model of the system. So here we assume that we already know the mathematical model of the system, but we want to use reinforcement learning, and in particular Q learning, to address some issue. Okay, or to make the system satisfy a given objective. Okay, so first I will start by brief introduction to what does Q learning mean for people that are not familiar with this concept. Okay, so in Q learning we have an agent, for example, a robot that I'm representing here by this emoji, and you have an environment. Okay, for example, this is my environment here. It consists of different states. It consists of these two obstacles that I want to avoid, sorry, and it consists of this target region that I want to reach. Okay, and then the objective is to master the selection of actions to optimize the reward. So I have a reward that I will be defining later, and I have some sort of actions. For example, the actions here are simplified. They either go up, down, left, and right. Okay, and the objective here is start from this region, reach the target, avoid the obstacles while using the fewest possible number of actions. Okay, which means that I want to avoid the obstacles, but I want also to reach this target as fast as possible. Okay, so this is the general formulation of reinforcement learning problem. So from a mathematical point of view, this problem can be represented by the following way. So we have what we call a transition system. So a transition system consists of those elements. So we have a state space, which is set S. Okay, the set S here, which is represent the state space, consists of 20 states, either 1, 2, 3 until 20. I have an action space, which are the actions that, for example, the robot can take, which are either go up or down or left on the right. I have a dynamics. So what does the dynamics mean? It means that if I start from state and I apply a given action, what will be the next state? For example, if I start from the state 7 and I apply right, the next state will be S8. If I start from 7, I apply left, the next state will be S6. Okay, so I have a reward which allows me to measure somehow how good a state action pair is. Okay, for example, the reward here is 20. It's 0 if the state or if the next state is equal to 20. So once I reach this target, which means that I satisfied my objective, I'm giving a very good reward. I'm giving very bad rewards to penalize my robot, for example, if I collide with those obstacles, S9 and S12. And I'm giving -1 otherwise, because I want to reach my target as fast as possible. Okay, and I have a discount factor. Okay, so this is a general formulation of what is called a Q-learning problem in reinforcement learning. Okay, and what is the objective? The objective is to construct a policy. Okay, so it's a policy or a controller. Okay, so it's a map that allows me to make decisions. Okay, so it's the policy that, for example, measure the states and tells me which action I need to apply, which actions I need to take. Okay, and then based on the policy, I can get what I call a trajectory or a path. For example, if I start from the state SK, I can apply input AK, I move to the next state SK plus 1, and the reward will be GK plus 1, and then from SK plus 1, I apply an action, AK plus 1, etc. Okay, and I keep evolving. And then to move how good a couple of state S and action pair are good, I'm using the concept of Q value function. Okay, so this is the main concept in Q learning, and then the Q function is represented of the following form. For example, if the state here is S is equal to S0, so the Q value is given by gamma to the power 0 G of S0 A0 plus gamma to the power 1 G of S1 A1, etc. Okay, so here gamma is the discount factor. Okay, and G is my reward function that I defined here. Okay, and then using this formula, I can compute the Q value for this couple S and couple of state S and action A. Okay, and then in general, the objective is to find some sort of, the best or the optimal Q value function, okay, which is called Q star, and which satisfies this Bellman equation. And in general, we cannot resolve this equation directly, so we solve it sequentially. Okay, for example, for my robot problem, I have my states from S1 to S20. I have my actions from A1 to A4. Okay, and I start, for example, from this couple of state action here. Okay, so for this couple of state action, I initialize my Q value, for example, to 0, and then I use this update law, and I keep iterating. Okay, and I do this for all the couples state actions. Okay, all the state action pairs, I apply this update law, and then I keep iterating. And then the main advantage of Q learning is that if the number of iterations goes to the infinity, I will converge automatically to the optimal Q value. Okay, this is the classical approach in Q learning. But then the main issue with this approach is that it can be applied generally to discretized state action spaces. So I need to have some sort of tabular state action spaces. So the number of states needs to be finite, and the number of actions needs to be finite. So that I can apply this approach in a direct way. Okay. And then the question we're asking ourselves is, what if the state and action pairs are infinite, which is for the case, for example, in most of real life applications. For example, if a robot is evolving, it's not evolving in discrete space, it's evolving continuously. Okay. And then we have applied this Q-learning framework to what is called the van der Pol oscillator. Okay, so this is a very well-known mathematical model that is used to model different behaviors. For example, oscillatory behaviors in physics. It's also used in biology, economics, etc. So this model is represented by this difference equation, where here x is the state, it represents the position, and v is the velocity. Okay, and I'm having a control input here, u. And then what was the objective? The objective is to start from a region and then reach this state. This state considers position, which is 0, and velocity, which is 0. Okay, and then we use the following reward function. And then since we had a continuous space here, as you can see, the state space is continuous. The values for the position are between -2 and 2, for the velocity between -3 and 3, and for the actions are between -1 and 1. Okay. So what is usually done is that we need to discretize those states and action spaces before we apply the Q-learn. Okay. So we have been doing this. So we have been discretizing the state space and action space using different values. Okay, so those are the values of the discretization, but here you can see that we're never able to reach this target. We're never able to reach this within 0, 0. Okay, and here we're asking ourselves the following question. Aren't we able to reach this target because this problem does not have a solution? Okay, and if this problem does not have a solution, if the system can never reach this point 0, 0, then of course we can the Q-learning cannot also find a solution to this problem. Or do we need a finer discretization? Do we need to discretize more? Okay, and if we need to discretize more, how much do we need to discretize? Do we need to go to, I don't know, 100, 1000, 1 billion discrete points? So what would be the limit? Okay, and this is the problem we have been tackling here. Okay, so since we cannot use Q-learning in a continuous space, now if we want to achieve a given precision, how do we need to discretize our space? Okay, so I will skip those slides to simplify things, but then this is the main problem we have been tackling here. So we have a mathematical model, a difference equation described by this form, where x again is the state, v is the action, and we assume that the map f and then the reward map are Lipschitz continuous with some Lipschitz constants. And then the question here was the following. Okay, so now since my space here x belongs to Rn, which is continuous, and the action belongs to set A in Rm, which is continuous, I need to discretize. Okay. Now, if I want to achieve a given precision epsilon, okay, if I want the Q-learning scheme to be epsilon optimal, how much do I need to discretize my space? Okay, how do I need to discretize both the state and the action spaces? Okay, and to address this issue, I have been using symbolic control. Okay, as I said, so symbolic control, how do we proceed? We start from a continuous space, we discretize it, we run the Q-learning on the discrete space, and then we transform the guarantees from the discrete space to some guarantees on the continuous space. Okay. So now one of the first challenges we faced is how to deal with non-determinism. Okay, because here's the thing. So the classical update law for the Q-learning scheme is based on this equation. Okay, and in this equation, we can see that I have a term here, S prime. And what does S prime mean? It means that S prime is the states that I reach if I start from the state S and then the input A. For example, if my robot is at position S and I apply a given action, then at the next step, my robot will be at the position S prime. And it will be in a unique position. Okay, the robot, if it starts from a position, I apply an action, it will move to a unique position. It will not move to multiple positions. But in the symbolic approach, what we do is that we start from the set. Here we discretize the space. We start from this discrete state here. This is the reachable set. In intersect we do 3 regions. I'm having non-determinism. I can go from this discrete region and do 3 discrete regions in parallel. Okay, so when I'm going through the abstraction, I'm in non-determinism. I do not have a single successor here, S prime, but I'm having 3 successors because I do not know if I can go here, here, or there. Okay, and then the first contribution here was to create 2 Q tables. Okay, so we're using a minimal Q table with the following update law and the maximal Q table with the following update law. So this Q table is taking the worst case scenario with respect to all the successors, and this second Q table, Q overline, is taking the best case, the maximum, the best case scenario with respect to all the successors. Okay, and then based on this result, so we first showed that those Q values, the minimal and the maximal ones, that they're optimal, they are unique, and they converge to a unique solution. But we also, so one point here before I forget is that now again, for this update laws, since I need to do this independently for each stage and action space, here also we can use GPUs. Okay, we can parallelize this procedure and use GPUs. So if we have access to HPC platforms, this will be very, very good in terms of computation, since we can deal with those procedures and then compute those Q value functions in a very efficient way in terms of memory and in terms of computation time. Okay, and then, so now once I can compute those minimal and maximal Q values, we had our first result. So what does this result say? It says that I have the true Q values. These are the true Q values for the infinite space that I cannot compute, because the space of states and of actions is infinite, so I cannot compute this. But I can discretize and compute this minimal and maximal Q value functions. Okay, and then we have shown that this Q value is always bounded between this minimal and maximal Q values function. Okay, this was our first contribution. But then we may be in the case where the true Q value will be between the minimal and the maximal, but then the distance between the minimal and the maximal is very loose. Okay, for example, the minimal Q value for a given couple of states and action can be, I don't know, equal to -10 to the power 6, and this one will be equal to 0. Okay, so since the distance between these two values is very big, I mean, this result here is not that much powerful. Okay, and it needs something more. And then this is what we're able to provide in the second result. Okay, the second result, it states the following. It says that now I have my space or my problem that is defined on a continuous space. Okay, I have the true Q values that I cannot compute, and I can compute the Q underline and the Q coverline, the minimal and the maximal Q values through the abstraction. Now, if I fix a precision epsilon, and again, the precision will depend on the application, but once I fix my precision epsilon, if I choose the discretization parameters values eta and mu, so eta is just the number of discrete states per dimension, and the mu is just the number of discrete inputs per dimension. But if I choose eta and mu according to some formulas that depend on the Lipschitz constant of the system and the reward, etc., then I can ensure the following. I can ensure that the distance between the minimal Q values and the maximal Q values is bounded by epsilon. and which implies also that the distance between the true Q values that I cannot compute because it's defined for an infinite state action space, and the maximal or the minimal Q values that I can compute is bounded by epsilon. So this is the difference here, that once I fix the precision epsilon, I have some sort of expression that tells me how do I need to discretize my space to achieve this precision. Okay, and then we have been applying this to some few case studies. So the first case study was a mountain car problem. So this is one of the main problems, very famous problems in the reinforcement learning community. So it's a car that is represented by this following dynamics, where the state consists of two variables, so the position and the velocity. And we want the car to start from position and then reach this flag here. So the flag is at the position 0.6. Okay, and then if we throw the car here from given initial condition, it will not be able to reach this flag. But then what is the right strategy? The strategy is that the car needs to keep oscillating here until it gets enough momentum, and then it can go and reach this target here. Okay, and as you can see here, the position is defined on a continuous space, the velocity is defined on a continuous space, and the action also is defined on a continuous space. So I've been fixing the precision here, epsilon, and then using our formulas, we have that here, yeah, this was the distance or the step of the discretization for the state space and the step of the discretization for the action space to achieve this precision. And here our simulation. So here, this is the evolution of the position of the car as a function of the time. And you can see that we can reach the point 0.6 after 550 times steps. And those are the actions, the evolution of the actions with respect to time. And as you can see here, so this is the table that's showing, for example, how the precision affect the discretization. And you can see here, for example, that it's naturally the more precision or the better precision we need or we want to achieve, the more we need to discretize our state space. For example, if our precision was 2, then we require 40 discrete states and 3 discrete inputs. But if we want a precision of 0.86, then we need to have 160 discrete states and 12 discrete actions. Okay, and then we have been applying the same approach to the van der Pol oscillator problem that I presented previously. And here, so these are the simulation using the classical Q learning scheme, and those are the simulation using our symbolic Q learning scheme, which is the one that we go construct the abstraction, proceed with the Q learning for the abstraction, define the precision, and then based on this precision, discretize the space and get a controller using the Q learning. And we can see here that we reach some sort of neighborhood of this target point. Okay, so to conclude, so I did a brief introduction on what are cyber physical systems today, why machine learning for cyber physical system is challenging. And it's challenging because we need guarantees. Okay, for example, if you have a car, if you want to use machine learning to control a car, you cannot just run a machine learning algorithm and then saying, okay, it will work. No, you need to have proofs, mathematical proofs, algorithmic proofs to show that nothing bad will happen. For example, if you have a robot, again, you want to control it to do some objectives, and you want to use learning, you need to have proofs that the robot will avoid a collision with obstacles and that nothing bad will happen. And this is one of the main challenges in the control or the use of machine learning to the control of cyber physical systems. And then I presented the concept of symbolic control. As I said, symbolic control is that we take the system from a continuous representation to a discrete representation. Okay, and then I presented some sort of complementarity between symbolic control and machine learning, in the sense that how we can use, for example, machine learning to solve an open control problem, and which was explained in the first scenario, or we have a model with, or we have a system without a mathematical model, and we have data points, and we want to construct an abstraction and then a controller based on data points. Okay, and then to have guarantees, we need to use some tools from statistical learning to provide some sort of probabilistic guarantees. And then in the second problem, we have a Q learning. Again, the problem is how to discretize the space to be able to use Q learning in a safe way. Okay, what do I mean by a safe way? In the sense that we have some sort of accuracy on how the Q learning scheme is good. You have some sort of measure on how the Q learning scheme is good. And then to deal with this issue, we have been using tools from symbolic control. So that's all from my side. So those are the main papers where those works have been developed. So if you want to go more through the technical details, so in the presentation I avoided the technical details, but if you want to go and read the proofs, etc., you can find them in those three papers, which are already available on archive. And those are the main collaborators I have been working on this topic. And thank you for your attention.
Thank you very much, Dr. Adnan, for this talk. It was actually amazing with all the details you presented, and you actually made it very enjoyable for everyone, including people who do not have a background in cyber-physical systems or in machine learning, because you made everything so clear. You actually laid the ground for the problem, for the approaches and everything. So it was actually amazing. Thank you very much for this talk. So before we move on to the questions from the audience, we have Dr. Ayman Qisami here with us. So, Sayma, do you have a question for Adnan?
So my question, thank you Safa for making this webinar, and thank you Adnan for this nice presentation. So I did understand too much things with you. Thank you. So so my question is like did you I don't know if you are aware about physics informed neural network. So we use both PDEs and data to like to train a model and so on. So have you tried this approach or not?
No, so yes, so far I haven't been. Yeah, I have seen some work about these topics, but I haven't explored this. And because mainly, I mean, the type of mathematical models I'm particularly focusing on my research are more, differential equations, finite dimensional model. While those stuff are been mainly developed, for more general infinite dimensional PDEs, etc. But yeah, so to be honest, I mean, I don't know how is the state of the art in that domain. I'm not aware if there, for example, that's some results that tells you that okay, you start from data, you have some data, and you have some sort of model, and you want to combine both the physics of the model with the data. But what are the type of guarantees you can get at the end? And I think
So there are no guarantees. So the idea is just to like to modify the loss function and combine both
yeah,
physical
I,
laws and data. So yeah,
yeah,
this
I
is
think what would be interesting is to explore to this sort of directions, on
Mm.
how you can get guarantees at the end that when you are combining both, you're having some guarantees, for example, that the true model of the system, which corresponds to the reality, and what you are learning is bounded by something, by precision that you fix a priori.
Yes, this is yeah. I think this is the thing. So coming back to the Q learning, so and the HPC. So I think you are aware that like HPC platforms are composed about thousands of nodes, and the idea the idea maybe is how we can apply the Q learning on optimizing the resources. Like for example, we have these thousands of nodes, and the target maybe can minimizing the throughput and minimizing the energy consumption and ensuring that tasks meet their deadlines. So, in your opinion, how we can apply this Q learning model to this kind of thing?
Uh, yeah, so I would say so. So here, because the Q learning is it's something that can be parallelized in general. Okay, so the training can be parallelized. Okay, and since the training can be parallelized, so you can run different parts on different. So if you can see this if I get back to the formulas here, so now it depends on the given state action pairs. And since you have multiple state action pairs, you can keep exploring, each of them somehow in parallel. Okay, so this is mainly what we have been doing. For example, in this paper with Sadek bin Fatal Alawi, so he implemented this on the on Tubqal on the super or HPC platform that we had at UM6P.
Okay, now if you want to like to apply this approach, but in optimizing the resource utilization in HPC, uh, so do you have any like kind of idea about how we can do that?
Optimizing
Like we have
resource.
some targets. Targets maybe can minimizing energy consumption, minimizing the throughput, and like ensuring that the tasks will be executed. So, in your opinion, like this how we can apply Q learning in this?
Okay, yeah, I would say the simplest, to be honest, I would say, I mean, the simplest, I'm not sure yet if it will work now, but I would say the simplest or the straightforward answer would be uh, uh, to add those as cost functions in the reward itself. Okay, maybe incorporating those as in terms of the reward, in terms of the cost function. I mean, in some sense, during uh, the training will consider them, while learning the control strategy, for example. Okay, but I have seen some works, some other works, not exactly in reinforcement learning, but more in control, where, for example, you have, I don't know, you have a robot, or you have multiple robots, and you want those multiple robots to achieve some objectives okay, to collaborate to achieve some objectives. But then those robots, for example, they can in some sense uh, use, for example, some processors just for predefined period of time. They cannot all access to the processor at the same time. Okay, and then there is this sort of I would say complementarity between how you would schedule, okay, the robots to access to the computation platform to meet their objectives, but also how you can achieve the global objective. But also, if you want to relate this more to reinforcement learning, you need to relate it more to multi-agent reinforcement learning. In multi-agent reinforcement learning, there are these issues when, again, there are different agents. You want to train them, okay, and you may have some sort of common or shared resource, and then you need, during the training, or how you somehow you need to incorporate scheduling with the training, because not all the robots will have access to the I would say the computational platform. So there is some sort of complementarity between specification or the objective you want to achieve and the scheduling procedure. So I hope it replied to your.
Yes, yes, yes. Thank you, Adnan. Maybe we can discuss later on
Yes.
more details because I know that Safa is aware also that, for example, in HPC platforms we use some deterministic like functions to decide which user will take which resource and so on. Maybe like implementing some like approaches like the ones you did in your study. Maybe it can improve the resource management. Okay,
Yes.
thank you, Adnan, again.
Yeah, I actually agree because at some point we can deal with the resource management as also an optimization problem at some point. Yeah, with an objective function, so we can apply whatever applies on a regular optimization problem. All right, so let's take a question from the audience. We have a question from Hamza. So I think Hamza is more asking for an advice. So thank you for your course. I have one question. How can I apply machine learning in material science? And tell me if I must know all this for my application or learn just application machine learning.
Yeah, so to be honest, I mean, yeah, I think I know nothing about material science, but I would say that, yeah, that my general advice is that when you're trying to study machine learning, it's always good, to try to learn the mathematical background behind the machine learning, because that's what makes difference between, I would say, good researcher or good engineer and the developer. I would say that a developer, for example, he can apply tools from machine learning. For example, he can train neural networks, etc. But I would say a more or a better developer would be the one that is able to understand, the details behind the training procedure, for example, uh, of neural networks, the mathematical details, so that if he got a wrong answer or a bad answer, or if he didn't get the result that he's expecting to get, he's able to understand and modify his training, he's able to play with the parameters, etc. I would say that the general, I would say, advice. I mean, it's good to learn how to implement algorithms, but it's better to also try to touch a little bit the mathematical details and understand more in details how things are working.
Yeah, this is actually very important because for the most part, a lot of people deal with those models as a black box.
Yeah, that's
So, yeah, so like some pre-implemented or pre-trained even models, and they're just using it. And then when, as you said, when the outcome is not correct or when the accuracy is not there, so is it a data problem? Is it
yes,
a model problem? So you're actually confused. So you don't know where to go. So, but if you have the basics of the math behind, so at least you can rule out some stuff, and then you
yeah.
can take care of the rest. Yeah, so we have another question from Rizlan. So she's saying, thank you, sir, for your presentation. I have one question. How can Gaussian processes be applied to model uncertainties in cyber-physical systems while guaranteeing stability and prescribed performance in control design? Control design.
Okay, yeah. So this is indeed what we have been doing, for example, in this paper. So I didn't get the time to present it too, but what we have been dealing with in this paper is how to start from data points, and then under some assumptions, okay, under some assumptions, uh, learn a Gaussian process type representation of the model with some sort of guarantees. Okay, in the sense that we know that the model or the distance between the real model and the Gaussian process will be bounded by some fixed precision that depends on the data. But again, here, the challenge will be on how to make those mathematical condition. For example, we have been relying on reproducing kernel Hilbert spaces, and then you need to make the assumption that the mathematical model can be generalized by what is called the reproducing kernel Hilbert space, and that you have some knowledge of some upper bound and the norm of this Erkaches bound of the real model system. So there are some sort of mathematical and technical details that you need to have in order to be able to use this type of tools, especially Gaussian process type tools. But in general, I would say, yeah, if you have those mathematical details, it's better to use this type of approaches, because with this type of approach, you are generally you have been just dealing with one probability. While on this more general approaches, for example, like the one using pack learning, we have two probabilities. We have the accuracy and then the confidence. But it presents the advantage that we do not have that much assumptions. This is I would say, the trade-off between this type of model in this paper and the one in this paper is that depending on the assumptions that you want to put. So the more assumptions you will put on the system, I would say the more accurate the results you will be getting at the end.
Okay, thank you. We have other questions. Yes, Yassine Kali is saying thank you. Sorry, he's saying that is an excellent presentation. Send in my warm regards to my colleague, Professor Adnan. Atman Sharqawi, Takaki, if I'm not if I'm not mistaken, he's saying excellent presentation, Prof. Saud. And we have a question from Lady. She's saying, very interesting and insightful webinar. Thank you, Dr. Adnan. For my question, what are other models we can use besides ML and Q learning for control?
Besides what, sorry?
Besides ML and Q learning for control.
Sorry, yeah, I mean, I didn't get the question very well. So do you mean the model for the system or the model for what exactly?
Lady, if you can just follow up on your question. Okay, let's take another question in the meantime. So Yassine is saying, thank you very much for your talk. Currently, I'm working on a network verification using formal methods. I think it is mandatory to start developing some assurance methods for reliable apply of machine learning, I guess.
Yes. Yeah. I agree. I mean, this is all. I mean, what we do research on, especially control of cyber physical system is we're not just using machine learning to learn how to control systems, but we're also trying to come up with proofs of guarantees. Okay, for example, I don't know if you want to use a robot to do some sort of chirurgical operation. Okay, I mean, you cannot just use machine learning and say I will trust my robot. Okay, or if you are, I don't know, if you are building a robot that you will send on the moon and you are investing billions of dollars on this robot, you cannot just say, okay, I will trust my data. No, you need to have some sort of guarantees that what you are getting or that the use of the data will be safe, in the sense that you are getting what you are expecting.
Okay, thank you. We have another question from Al Hussein. He's saying, thank you, Professor Adnan. Just I would like you to clarify the problem of the number of this, I think he means discretization, and why so now there is no Condi to know that.
Why so now? There is what?
There is no, I don't know if it's a typo, but I can't seem to understand it.
Okay.
It's there is no condition to know that.
Oh, condition. Okay.
Yeah. So here's the thing. So the thing is that when we start from this problem, what people were doing usually is that they start from the model and they discretize. Okay. As for example, I have been presenting from this model. So discretize with 10. If it's not working, they keep discretizing until it will work. Okay. But then we're asking the following question. Okay, if we need to discretize, we need to know a priori how much we need to discretize. And if we want to know how much we need to discretize, this is why we went through this procedure. So we start from a precision epsilon, and then from this precision epsilon, we had this formula on what should be the number of discrete states and discrete input to achieve that precision epsilon. So that at the end, you are having a Q learning scheme, but which is also epsilon optimal. And why the epsilon optimality is important? Because, for example, assume that you want your robot or your model, for example, here to start from here and to reach this region, okay, or to reach this point here, 0, 0. Okay, now assume that your precision epsilon is 10 to the power minus 6. And then with this 10 to the power minus 6, you are not able to reach this region. What does this mean? This means that you cannot resolve this problem with Q learning. Okay, this means that there is no hope you can solve this problem with Q learning. And this is the strength of the approach. It gives you an answer to the problem. Okay, without this approach, what you would be doing, you would just keep discretizing, but keep discretizing. To which discretizing, or how much is the discretization you will need to achieve to say that, okay, if I can find a solution or I cannot find a solution. Okay, you need to have some sort of limit, and this limit here is formalized by this precision epsilon.
Okay, thank you very much.
To follow up, so Adnan, sorry, Safa. So this
Yeah,
epsilon,
sure.
how we can choose this epsilon? So it depends on the problem,
As I
or?
said, it depends on the problem. For example, I don't know if you want. I consider it one example. For example, if you have a robot that is moving, okay, in a very small region, then the precision should be on something that is in centimeters. If you have a robot moving in a very large space in a city, or in a very large space, then the precision can be in the magnitude of meters. It depends on the application on that you are working on, that you can see that. I would say the expert of this application will tell you, or will tell you somehow, this is good precision, this is bad precision.
Okay, my last question is mathematically the guarantee. What does mean guarantee? It's like unicity of the solution, or something
Yeah.
like that, or
The guarantee here is that now we start from precision epsilon. Okay, you discretize the space. The Q-learning scheme on the discretized space is epsilon close to the Q-learning scheme on the continuous space that you cannot solve because the space is continuous.
Mm.
Okay, but you guarantee this precision epsilon, which we showed here. So you're guaranteeing this precision epsilon. You will achieve this precision epsilon.
Okay, got it. Thank you, Adnan.
Right. Thank you very much, Dr. Adnan. Thank you very much, everyone. Thank you for the attendees. We had a lot of questions. We had a very nice interactive session. It was actually amazing. So our webinar will still be available on YouTube, so you can always go back to it and check whatever Dr. Adnan presented. And yeah, thank you very much again for accepting my invitation. Thank you for giving us your time and for sharing with us this knowledge. We do really appreciate it.
Yeah, thank you very much, Safa, for the invitation and for taking care of organization and for all this wonderful initiative. And
yeah, it's my pleasure. Thank you very much again for being here. Thank you for the audience, and I wish you all a nice weekend.
Okay.
Bye.
Goodbye. Thank you, Safa. Thank you, Adnan. Assalamu alaikum.
Thank you all. Bye.